Welcome to ECE 302. This is lecture 3.5 on moments and variance. I am Professor Stanley Chan. In the last lecture, we started to talk about the topic on expectation. And we went through some of the basic definitions of expectation. In today's lecture, we're going to learn more about expectation. In particular, we want to know more about the properties of the expectation. And then we will also talk about a topic on moments and variance. There are four properties of expectations that we will need for our course. The first property is that if you have a function g, and if you calculate the expectation of g applied to x, you are not changing the probability mass function. What you're doing is that you're just changing the state that you're working on. To explain this property, let me draw you a diagram. Here is a function y equals to gx. And on the x-axis, I'm showing you all the probability masses. When you try to apply this mapping, we define y equals to g of x. Then where will the y be located? You look at this curve, and then you send all these arrows to the corresponding y's. And here will be your y's. So what is expectation? The expectation is computed as the state times the height plus another state plus another height, and so on. So when you try to calculate the expectation of gx, what you need to do is to calculate the state times this height plus this state times this height, and so on. Because the probability of getting an arrow is not changed with or without this mapping, the height of these arrows will remain the same. However, because of your function, the location or the state of the arrow will become different. For example, your state is here, and then when you go through this function, the state becomes there. Therefore, in this equation, you can see that I'm still taking the summation. We still have the probability mass. However, the state values will become transformed. That explains this property. When you apply any gx to, before you do the expectation, you will get this. A very simple example is that expectation of x squared would just be summation of x squared times px. Or expectation of sine x would be summation of sine x times px. Or expectation of square root of x, that would just be the summation of square root of x of px. Certainly, you're summing over all the possible states of x. The second property is that if you have two functions g and h, then applying the expectation to this sum of gx and hx, you can just do this expectation individually for everyone. Now, this can be very easily proven according to the definition. Here is your gx plus hx, and this is the summation of gx plus hx times px. This is your probability mass function. This is your state. And here, since you have a summation inside, that you have adding h and g, this can actually be broken down into two halves. And sum of hx and px. Okay, and this is clearly expectation of gx. This is the expectation of hx. So, for example, if you have expectation of x squared plus 5x. This is the same as expectation of x squared plus expectation of 5x. The third property is that if you multiply the random variable x with a constant, the constant would come out. The proof is that if you have a c times x, you just need to look at this cx times this px. And c can come out of the summation, so you have x px, and this is just c times expectation of x. Now here is a very easy diagram to visualize what's going on. Suppose that you have a probability mass function that looks like this. You have 0, 1, and 2 located at these locations. And then the average is at the center, which is 1. Now, if you move the random variable x by multiplying x with a constant c, what will happen is that this value would be translated to here, because this is a state of 0. 0 times c will stay as 0. But 1, let's say your c equals to 3, then 1 will map to 3, and 2 will be mapped to 6. Now notice that the change is only occurring to the states. The change does not occur to the height of the probability masses. And so when the probability remain unchanged, the mean can be calculated by just multiplying the constant c with the random variable. So what you can see here is that since my state 0, 1, 2 becomes 0, 3, 6, my mean will just be this mean, which is 1 multiplied by 3. The last property is what we call the DC shift. Suppose you have a random variable x and you add a constant c to this random variable, then the expectation of x plus c will just be the expectation of x plus the constant c. And here is an illustration. Suppose you have the same PMF as before. You have 0, 1, 2. You have probability mass functions like these. And now what you're doing is that you grab this entire impulse train and then you move them to the right or to the left by a constant c. So here I am moving all the values from 0 to 5, 1 to 6, and 2 to 7. I'm just shifting all these impulses to the right. Alright? Okay, then you can show that the expectation of x is the same as the summation of x plus c, and then px, and then here you will have expectation of x times px plus the summation of c times px. But c times px is just c because the summation of all the px will give you 1, and therefore this will give you expectation of x plus constant c. So this concludes the discussion on the properties of expectations. Now we are going to move on and talk about one more topic, which is the topic on moments and variance. So to start with, I want to define the term called the cave moment. And this is just applying property 1 by this definition of gx equals to x to the power k is the cave power of the random variable. So if you plug that in, you can show that the expectation will take this form. Here is a very simple example. If you have the probability mass function given by these, then the second moment, which is expectation of x squared, is x squared. So this is, you have the state, which is 0, because the first state is 0, and then you want to take square, okay? And then what is the probability of getting that? It will be 1/8. And then what is the second state? The second state is this number 1, so 1, and then you need to put a square. The square comes because you're looking at x squared. The probability of getting that is 3/8. And then you have 2 to the power 2. Again, this 2 comes from here, and then this 2 comes from your power. And then this is 3/8, and then 3 squared, and then 1/8. Okay, so that will give you 0 plus 3/8 plus 12/8 plus 9/8. Okay, so now you can do the simple calculation and complete this calculation. So cave movement is a very simple example of the properties of expectations. And with the moment in mind, we can now define the notion of variance. The variance of a random variable is defined as this. It is the expectation of x minus mu squared, where mu is the mean of the random variable. Now, it is called a variance because you can see what this term really is. It is the deviation of your random variable x compared to the center, which is the mean. And then you're taking the square outside, and so you are eliminating all the plus sign and the negative signs. And so when you calculate the square, you're measuring the deviation magnitude square. And then if you take expectation, you have eliminated all the possible randomness in x. That will give you a deterministic number, and that measures the spread of a random variable. So you can visualize that if I have a random variable that has a shape like this compared to a random variable that has a shape like that, this random variable will have a smaller variance. Okay, for example, like this, and then I have a random variable with this probability mass function, and that will give you a large variance. Okay, so now if you take the square root of the variance, then you will be able to get what we call the standard deviation. So the standard deviation is actually the square root of the variance. Okay, now let us work on example. Suppose x is a coin flip with probability of p, then what is the variance of x? So you know that the probability of x equals to 1 is p. The probability of x equals to 0 is 1 minus p. Okay, and so the variance of x will be equal to expectation of x minus mu. Okay, now what is mu? Mu is expectation of x. Expectation of x in this problem, it will be 1 times p plus 0 times 1 minus p. So that will give you p. Okay, so x minus mu square. So that can be simplified to expectation of x minus p square. That will give me expectation of x squared minus 2px plus p squared. And so now I also need to calculate this expectation of x squared, which is not too hard. So expectation of x squared is just 1 squared times p plus 0 squared times 1 minus p. So that will give me p. So I have p minus 2p times expectation of x, which will give me another p, and then I have p squared. So ultimately I will have p minus p squared. So this is the variance of this random variable x. Let me briefly talk about 3 simple properties of the variance, and then we can go back to the midterm exam problem that we introduced in the beginning of this lecture. So the first property is that the variance can be calculated using this formula. it says that on the left-hand side, you have the variance. On the right-hand side, you have the second moment minus the first moment square. Why is this true? It's true because the variance of x is defined as the expectation of x minus mu square, thus can be expanded to x squared minus 2 mu x plus mu square. And so now you will have expectation of x squared minus 2 mu of expectation of x plus mu square. And then this will give you the second moment. And then here you can see that this is also mu. And so you have a mu square, and that's a minus 2. But that will also get cancelled by this term, so you have minus mu square. Okay, so this is exactly the same as this equation. The second property is what we call the scaling. The scaling of a variance is the following. So suppose you have a constant c, you multiply with the random variable x, then the variance of c times x will give you a variance of x with a c squared coming out. Now, why is that true? Let us first prove the result, and then we can go back to the diagram. So variance of cx, it is the expectation of cx minus the expectation of cx, and then you take a square. Okay, so what is the expectation of cx? Let's just c times mu. It's a property that we have derived for the expectation. And so now we have expectation of cx minus c mu square. Then what is it? Well, the c square can come out, and so you have expectation of c square of x minus mu square. And since this c square has nothing to do with your randomness, the c square can come out, so you have c square times expectation of x minus mu square, and this is exactly the variance of x. Okay, so we have proved this result, but the pictorial illustration is even more informative. So suppose you start with this probability mass function. You have 0, 1, and 2 as the state. The variance is really measuring the spread of your random variable. Now, if you multiply the random variable x with a constant c, like this one, the 0 got maps to 0, 1 maps to 3, 2 maps to 6, so we're multiplying every one by a constant 3, then the height of the probabilities are not changed. However, the spread becomes bigger. And how big it is? Well, because you are spreading it out, you will have a constant that comes out. And according to the formula, this constant is c squared. Okay, so if you ever try to multiply the random variable, that constant will become squared when you calculate the variance. We can also ask what will happen to the standard deviation. So the standard deviation of c times x is the square root of variance of c times x, which is the square root of c squared of variance of x. And so this will give you c times the standard deviation of x. Okay, so if you're trying to measure the standard deviation, then applying constant to the random variable will just help you bring the constant out of the standard deviation without the square. One last property. This property says that if you add the random variable x with a constant c, then the variance remains unchanged. Now, why is this true? Because the variance of x plus c is the expectation of x plus c minus the expectation of x plus c square. And so you can see that this is expectation of something square, and this is x plus c minus expectation of x, and then minus c. This c and that c will cancel out, And so you will left with expectation of x minus mu square, which is the variance of x. The diagram here also illustrates the reason. Suppose the random variable has this probability mass function. Now, if you move the entire probability mass function to the left or to the right, you're just shifting them here and there. The spread of the random variable is not changed. Okay, so no matter how you move them, the random variable, the variation will remain unchanged. So now let's come back to this problem. If we add 10 points to everyone, then will the mean be changed? Yes, we know that the mean will be changed because we're adding 10 points to everyone. And so the mean becomes expectation of x plus 10. Will the standard deviation be changed? No, because if you move this entire histogram to the right by 10 points, the standard deviation will not change at all. And also, if the letter grades are curved, will this change the letter grades? The answer is also no, because the letter grades are assigned relatively between the student's score and the class. And so what you really care will be the standard deviation and not the mean. Okay, and therefore, I hope with all this discussion here, you have learned the meaning of expectation. You have also learned the difference between expectation and also the sample average. Expectation is calculated from the probability mass function. It is a quantity that comes from the random variable, versus the average is computed from the histogram, which is usually a finite data set. And there is a very, very important difference between them. We have also studied the properties of expectations, and we have also discussed a notion called a variance or standard deviation, as well as their properties. So I will encourage you to try our homework assignments. And if you have a question, please feel free to ask. We will do our best to help you. Thank you very much.